couple people, well, 3 people, I believe, contacted me about problems with the reading quizzes. The site's been having some issues. It's not your internet connection, as far as I can tell. It's their problem. The 3 people that contacted me were able to get them done, which relieves me. I'm sorry about the problems, obviously. Today we're going to learn about electric potential. Now, on the reading quiz, there was a question that actually Rebecca informed me about on Monday night. And early Tuesday morning, I told it not to use that question because the question was just incorrect. And still later in that day, Ashley got the question. So I have to remember to go through and regrade that one by hand for those who got it because it just has the wrong answer. And that question had to do with the difference in the words voltage and electric potential. Electric potential is synonymous. Let's change colors. Is synonymous with voltage. So if we're talking about electric potential, we're talking about voltage. Why do they call electric potential voltage? Well, it turns out the units of electric potential are volts. And so people start calling it voltage because the units are volts. So it starts with electric fields. I have on this slide 2 pictures of a charged particle and electric field. The one on the left is showing a positive charge. The one on the right is showing a negative charge. And we learned the equation from last week that the force is equal to Q times E. So if I have a positive charge, it's going to have a force that is in the same direction as the electric field. If it's a negative charge, it's going to have a force, but now it's going to be the opposite direction because the negative charge puts a minus sign. So it's going to have a force in the negative direction of the electric field. So in each of these cases, there's going to be a force in the particle. If I have a force on the particle, well, forces make things move, right? And if we have a force and we have motion parallel to that force, we call that work. And so the electric field is going to then cause a force that does work on a particle unless there's something keeping it from moving. And this electric force, like gravitational force, which has essentially the same equation, is a conservative force. What that means is if you do work against the electric field, so for instance, if I start with the little positive charge where it says low PE, and I move it against the electric field to the place where it says high PE, I've done work. I had to apply a force equal and opposite direction to the force of the electric field and move at a distance, so I did a work of the force I applied times the distance it moved. But if I let go, the electric force is going to return that energy, so I had potential energy stored up. All of this to say that we have electric potential energy, and so we're going to start doing some calculations with electric potential energy. But first, something akin to one of your homework problems. You have a homework problem that says the Earth has a surface electric field of 150 newtons per coulomb pointing down. And then it says, while this charge is spread out roughly over the surface of the Earth, if you have a spherically symmetric distribution of charge and you're outside of it, you can treat it as if all of the charge is at the center. So for that problem with the Earth, I'm actually going to do the Earth problem instead of this first, just to make sure we get that clear. So we have the Earth. So we have the radius of the Earth. And then we have electric field lines that are pointing into the Earth at the surface. With a magnitude of 150 newtons per coulomb. I didn't talk about the units of electric field when we spoke about them on Friday. But I did say that electric field is defined as the force per charge. Unit of force is a Newton. Unit of charge is a Coulomb. So electric field has units of newtons per coulombs. First thing you should be able to tell me, what sign is the charge on the Earth? The charge is on the surface, yes, but whether it's on the surface or throughout, because of the spherical symmetry, we're just treating it as if all of the charge is at the center, even though it's on the surface. What sign does it have? Okay, I have a bunch of negatives. Christian, why? Because it's going in. Electric fields point into negative, out of positive. Why? Because electric field is showing us the direction the force would be on a positive point charge. So if I bring a positive point charge close to a negative, it's attracted, pulled in. So that tells us that it's negative. So we start with that. The Earth has a negative charge. And then we say, if all of that charge is at the center, treat Earth as a point charge, then we can find the electric field is kq over the radius of the Earth squared. And so if I want to find the q, it's just electric field of the Earth times the radius of the Earth squared over k. I'm not going to do the calculation. I actually did it and then realized everyone has the same numbers and erased the answer. So at least you have the opportunity to do your work there and find what the charge is on the surface of the Earth. And then there's a couple questions about the force on a particle for that homework problem. But just wanted to look at that, just a very practical thing. This is actually real. People in the Physics 252 have a more complicated variation on this problem. Right? I think it's problem 5 in that homework set. Now let's look at this. A thin metallic spherical shell of radius r carries a total charge q. That's just like what we did, right? Which is positive. Whoop, that's the opposite. The charge is spread out evenly over the shell's outside surface. Sketch the electric field lines in two different views of the situation. One, a spherical shell is tiny and you're looking at from distant points. That's what we're used to. That one, you're out here. If this has a positive charge, what are you going to see for the electric field lines? Going out because they come out of positive. So you're just going to see something that looks like that for part A. So here's the solution for part A. For part B, it's a little different. For part B, you have positive charge all out here. But you're inside. What's the electric field going to be like there? Okay, there's really there are three options. We know the electric field lines have to be always normal to a surface, right? If they're not normal, then the charge is just going to be moved around until they become normal. So the electric field lines would either have to be radial inward, radial outward, or zero. So if we had electric field lines going like this, where do they start? Have to be at the center, but what's the charge at the center? If all the charge is on the exterior and there's nothing at the center, what's the charge at the center? Zero. And thus, how many electric field lines should come out of something with a charge of 0? None. So that can't be right. Well, what about the other option? What if they're coming in? Then I have all the lines coming in, and electric field lines have to terminate at a charge. But there's no charge there. So what's the only option remaining? The only option remaining is there is no electric field inside of the conductor. That's the only way we can obey our rules of having electric field lines start or end at a charge. If there's no charge there in the center, and they have to be starting and ending at charges, with our spherical symmetry, it's got to have a 0 electric field inside. Now, when we learn Gauss's law, which will be very fleeting in the Physics 152 class, we'll see a very simple calculation to show that. So the electric field inside is going to be 0. So this here was the correct answer for what it looks like if you're inside. Kind of an interesting outcome, and that explains, I know at least one person was talking about a Faraday cage. If you are inside a conducting object, like let's say a bird cage made out of wire mesh, what's the electric field inside of that bird cage? If it's conducting all around the exterior, it's going to be 0 electric field inside. So what if lightning strikes that bird cage and you're inside? You're perfectly protected because all of that electricity is going to pass on the outside, leaving you fine and dandy inside, to at least a reasonable approximation. If everything was static electricity, that would be perfectly true, but of course lightning strike is not static, is it? So when you have moving charge, things are slightly different. But that's the whole idea of a Faraday cage. So you might have seen pictures of a guy with a typewriter in this thing that looks like a big bird cage with huge Tesla coils and just enormous arcs flying by, hitting his bird cage. And he's in there fine as can be because he's protected because he's inside a conducting chamber. Still kind of scares me, but the idea then holds true. If you have a metal body car and it gets struck by lightning, if you're inside, you're pretty safe. Now, if you step out, then you have problems. So ER is a long ago show, but they had an episode where there was an ambulance that had a power line on it. And so the ambulance was, at high voltage. But there's a patient inside that needs immediate help. And so I believe it was Dr. I don't know why this character, who takes a running start and jumps to get in so that he never forms a bridge between the electrified ambulance and the ground, which is actually pretty reasonable. He would still get a nice shock because he's going to go from no charge to a charge in there. But it's just going to be a very fleeting thing and not a continual current going through his body, which is what kills you. So it was probably good physics. Now there's another one that was just funny. The same person, Noah Wiley's character, was using the defibrillator. How many people have used a defibrillator? Okay, a couple. The only person I used it on is the only patient I ever had. Well, yeah. The guy was dead long before we arrived. Anyway, using a defibrillator, I've used a lot on dummies, not people that are not smart. And the funny was, Noah Wiley's character leans on the metal gurney while somebody else uses the defibrillator. Things you need to know if you ever use a defibrillator, like, emergency in the airport, they have the emergency defibrillators. Don't put it on somebody's clothes. If you put it on their clothes, what are you going to do? You're going to cause their clothes to catch fire. It's bad. You put conductive gel on the skin and you put the pads on that conductive gel. You want to have good contact. And you don't want to have contact with the person yourself or you get shocked. Okay, so just, things to be aware of. In an emergency situation, you're like, I've taken physics, I know some things. You don't want to then look silly. Okay, electric field. If I have two parallel plates with charge on each plate, it will create an electric field between them. If I have big enough plates compared to the separation, then it will make a nice uniform electric field. So we like to start things with these parallel plates. And these parallel plates, if you have here plus Q on one side, minus Q on the other, it will make an electric field that's equal to the charge on one of the plates. Notice it's the same charge on both. One's positive, one's negative. Divided by epsilon 0. What's that epsilon 0? We've used it before. Does anybody remember it? 8.5 something something times 10 to the minus 12, I think. It's the permittivity of free space. It's basically a number that tells us how easy it is to pass charge through a vacuum. And then the area of the plate. So once again, Gauss's law makes it easy to calculate this. That is the last problem, essentially, for the people in Physics 252, that calculus problem. So we have an electric field, a uniform electric field between the plates. That goes back to the picture I started with in the lecture, the parallel plates. So we have an electric field, and I've put a charged particle in there. It'll have a force. This is the charge multiplied by the electric field. And of course, if I have an unbalanced force, the net force is mass times acceleration, according to Newton's second law. So it will accelerate. And you have a number of homework problems that are utilizing this relationship, Newton's second law, and the definition of force to tell, hey, what's the acceleration going to be? And you get fantastically large accelerations for electrons and protons in electric fields. Just in case you look at the numbers and say, there's no way it's times 10 to the 13th meters per second squared. Yes, it is. So how is this going to be useful to us? Well, I'm going to skip right over that and talk about potential energy. And I know at least some of you watch the Khan Academy videos, the textbook links, on the relationship between potential energy from gravity, potential energy from electricity. Why the contrast between the two? Because we have virtually the same equation for force. So if I have a negatively charged Earth and a positively charged object, I'm going to have an attractive force between the positively charged object and the Earth. That is exactly analogous to having an object with mass near the Earth. Gravitational force is always attractive, so these are chosen to be opposite charges to make it attractive as well. So with this object here, if I take the object and I raise it from this elevation to this elevation, I did work on the object. And what happened to its potential energy is I did work on it. You do work on it to move it against the force, and it increases in potential energy. If I let go, that energy will be returned, why it's called potential energy. So as I raise that mass, the potential energy increases. So using our analogy, if I raise this charge some elevation, that is, I make the charge farther away, what happens to the potential energy? It must also rise. What's different about electricity versus gravity? Gravity is always attractive. So in gravity, when you separate things, the potential energy always gets bigger. When you let them come closer together, it always gets smaller. With electricity, if they're opposite charges, if you separate them, the potential energy gets bigger. But if they're the same charge, that is like two positives, as I move them farther apart, the potential energy drops. So that's what's different. Potential energy can work both ways because you have attractive and repulsive forces. So, give me a sec here. My theory is that this will now work and show me how many people answered, because I put in the dummy question with nothing in it. So, what direction does a charge move? Does it always move toward higher energy or lower energy, or higher voltage? We haven't talked about voltage, or lower voltage. Now, let me clarify. If you just release the charge, if it's free to move, not I'm manhandling it and force it to go somewhere, because then it just goes where you tell it to go. So people who haven't answered yet, Brandon, Angelina, Corso, Michaela. Okay. Angelina and Michaela. Do you not have yours, Michaela? It does not show as answered. Okay, it does now. It shows that you answered twice suddenly. Or maybe I just, yeah. And Angelina. Oh, no. Okay. So our answers were 8, 9, 0, 1. Pretty even match there. We have a plurality of always toward lower energy. Turn to your neighbor and discuss in great detail what do you think it should be and why. Meanwhile, I'll drop the ball.
Decided your sources, receipts.
I'm like, oh, I heard sources. Okay, let's go ahead and answer a second time. Okay, this time we had 4, 14, 0, 0. Okay, so people move toward the one that had the plurality. Angelina, since you didn't give it, well, not because, but I drew your card randomly. What do you think and why?
I feel like it's A.
Okay, feel like it's A. What's your reason? Okay. The reason I brought out the ball and threw it up and mentioned it was not because I was bored, but because everything in nature does the same thing. When I let go of the ball, it naturally goes to which energy state? Lower. That's what everything in nature does. That's a driving way of understanding how nature works. It goes toward lower energy. And so it's always going to go toward lower energy. Now, is that higher or lower voltage? That depends. But it's always going to go toward lower energy. Now this here is just cool. I've got to change screens because I don't have PowerPoint on the tablet. I haven't spent personal money for it, and since this is school property, yeah. Anyway, this is cool. This is an app that allows me to place charges, and the little arrows show the direction of the electric field resulting from those charges. So here I have a negative charge. How do I know it's negative? There's like 3 different ways. The one that I want you to focus on is that the arrows are pointing toward it. So I put the negative charge here, and then I can put a test charge and see what happens. So let's say I put a positive charge here. What's going to happen when I let go of a positive charge right there? It'll attract it in. Boom. Now that was boring, right? So let's reset this. And let's now put another fixed charge on here. Put a positive charge here. Now you see that the electric field lines are going from the positive to the negative, and you can see how they add up. In this case, they're the same charge. What's going to happen if I put it here and release it? My test charge. I show the electric field line. What's the force going to do, or what's the force going to be if it's in an electric field? For positive charge, the force is going to be parallel to the electric field because force is equal to QE. Oh, I forgot. You're looking at the other one. You can't see what I'm writing. So the force is equal to QE. So if I let it go here, it's going to have a force that goes the direction of the arrow. But notice what's happening. When it gets here, it most definitely is not moving in the direction of the force. Why isn't it moving in the direction of the force here? When you think about it, it's a simple answer, but at first blush, you tend to think it should move the same direction as the force. What does the force allow you to calculate? Acceleration. The force allows you to calculate the acceleration, and so at that point, the acceleration was going horizontally, but it already had some momentum that was keeping its motion from going that direction. So I can put my charge other places. You know, here it's a little more interesting. I didn't start right at the center, and so you can see it's wandering out. Kind of cool. And this has some presets. So here you see charges oscillating between like charges, or probably more fun, the wanderer. It's kind of in a trap. I say kind of because you'll see it does get out eventually. There, it got out. Okay, so that's, I just kind of like it. It allows you to see what happens when we have charges in the presence of other charges, as well as how the electric fields of multiple charges form up. Now, you had some homework problems. Just one more thing here. You had some homework problems where you had, I don't want to preset. Well, does anybody see a button that, yeah, okay. Here's a charge that's positive 1. Now let's put a charge that's minus a half. Here you can look at the symmetry and see that the electric field lines are pointing much closer to vertical above and below the bigger charge, much closer to horizontal above and below the smaller charge. You see the asymmetry, the bigger charge is going to dominate. So if you drew the electric field lines, you would have an asymmetry. You had a problem in your homework that has you, it just has pictures of one charge, another charge, and it asks you for the ratio of their charges. How in the world do you calculate the ratio of the charges if it just shows one charge, the other charge, and the electric field lines? Say louder, Angeline. Count the lines, because we know that the number of lines leaving or entering the charge is proportional to the charge. So you don't know the actual charge, but you can determine the ratio. And in that problem, you do need to make sure you pay attention to if the lines are going in or coming out. If the lines are coming out, which kind of charge is it? Positive. And if they're going in, it's negative. All right, let's switch back to my tablet. Now, electric potential energy. We calculate potential energy change based on the work done by a force. So the work done by a field, in this case it's the electric field, will give us a change in potential energy. So this here is, of course, the calculus equation for work. Work is integral of force dot distance. Without the calculus equation, what you did was work is force times change in distance. So this is the algebra version of the same thing. So if I have the charge, notice this is back to the figure I started the lecture with. If I have a charge that moves from here to here, then the force in that charge is QE, and the distance it moves is delta X. And so the change in potential energy is going to be minus the QE times delta X. And so that gives us an equation for the change in potential energy. But here's an interesting thing. Potential energy is very nice. We like to use it in kinematics. Remember, first semester, we learned first how to solve problems using Newton's second law. Then we learned how to solve problems using work-energy relations. And I told you, usually the work-energy relation is the easier way to solve the problem because work energy is scalar. You're dealing with scalar values rather than vector values. It makes life easier. In electricity, we really take that to heart. We don't like to use electric fields. We like to use electric potential energies. But we go a step further. We don't just talk about the electric potential energy. We talk about the electric potential. What's the difference in electric potential energy and electric potential? The names are so similar. You've probably already gone through it because of the reading quiz. But okay, I guess I have more discussion about the electric potential energy before I get to that. Electric potential energy rules. A charge has low potential when it goes to charge that is opposite because they're attracted. So a positive charge has low potential energy if it goes to a negative charge. A negative charge has low potential energy if it goes to a positive charge. So that means that a negative charge and a positive charge go the opposite directions for the same reason. They're both trying to go to the lowest potential energy state available to them. It's just which charge is going to be the lower potential energy state. Now we've learned Coulomb's law. Force is equal to K Q1 Q2 over R squared. So if we put it in the electric field form, the electric field is KQ over R squared. That's our electric field equation for Coulomb's law. What this says is the electric field is going to be approaching infinity as you approach any charge. As long as that charge isn't Q equals 0, the electric field is going to approach infinite strength as you approach the charge, either positive, infinite, or negative infinite. Now, when we talk about the potential energy change, potential energy was charge times electric field times change in position. The electric field's approaching infinity. Well, what do you think the electric potential energy is doing? It's also approaching infinity. So to calculate the electric potential energy, notice I have these calculus equations. You must use the calculus equations if the electric field is not constant. which is why we started with the simple parallel plates with a uniform electric field, because that's the only case where we don't have to use the calculus equation. But fear not. You don't have to know calculus. All you have to know is the solution to the calculus equation. So if I take this and put it in there, I have the change in potential energy is equal to minus integral of Q I need to label my two charges, Q1, K, Q2 over R squared dx. I have to pay some attention to my directions. I'm being sloppy with the directions here because how do you do this integral? Well, you've got to change from dx to dr. You do the integral of dr over r squared, you get minus 1 over r. And so it turns out that the change in potential energy let's see. One's positive, one's negative. Nope, like that. So the change in potential energy for two charges we calculated with this equation. Now, that's calculation of change in potential energy. You have to have two states for doing the change in potential energy. So that's what you get actually from the calculation, putting in the two limits. It's a change in potential energy. It's not a calculation of the actual potential energy because potential energy is defined by change. This is a place where the book kind of uses a wonky definition. You don't ever have the absolute potential energy. You always have it with respect to a reference place. To make life easy with electric charge, just like if we use Newton's universal law of gravitation, we define our reference when the radius approaches infinity. That's when we have two charges infinitely separated from each other. We're going to define that as zero potential energy. It doesn't have to be. It could be defined as 1 joule. But we choose to call that zero to make our lives the easiest. So we usually have a reference point of zero potential energy when they're infinitely far away. And then if I have two oppositely charged particles as I bring them closer together, the potential energy then will be potential energy with respect to that K, Q1, Q2 over R, which is what I wrote. And so if they're opposite charges, as it gets closer, the potential energy is dropping because of the minus sign. If they're like charges, potential energy rises as they get closer because you have the same signs for Q1 and Q2. So it's important to have these here because those are arbitrarily chosen standard definitions. Don't have to be true. They're just arbitrarily chosen standards. Our textbook makes a slightly different twist on that. So, and here's showing the actual work. You can see these are the equations I wrote down, except for I was careful with signs here. So here are graphs of what the electric potential energy looks like. U is just a symbol that some textbooks use for potential energy. And so if I have two attracting particles that has opposite signs, the potential energy approaches minus infinity when they're together and approaches zero when they're infinitely far away. If it's the same signs, then it's approaching positive infinity when they're together and zero when they're infinitely far away. So that's what the electric potential energy looks like, which we almost never use. we almost always use, just go past this, the electric potential. I went past those because we've already talked about lightning a bit. If you have several point charges, it can be confusing. First of all, we have an interesting idea of possession. What has energy? If I have this ball and it's up here above the ground, we say it has gravitational potential energy. And everyone always says, what object has the potential energy? We always say it's the ball. The truth is that it is the system of the ball and the earth that have the potential energy. It doesn't belong to one or the other, it belongs to both of them. And when I let go, they're both going to move to lower that potential energy, the earth by an unmeasurably small amount, and the ball by a very measurable amount. And so that's why we tend to think of it as belonging to the ball. When we talk about the charged particles, we don't have such asymmetries usually. We don't have one charge that's supermassive and one that's really small. And of course, the mass is a big part of it too. So when we talk about the charged particles, we have to be a little more clear. The energy is energy in the system, not for one of the particles or the other. So if I have two charges, it's pretty easy to calculate the potential energy. It's just K times charge 1 times charge 2 over the separation. But what if I have three charges? The easy way to think about this for me is to say, okay, let's start with just two of the charges. So I have these two charges. The potential energy between these two is such and such. Then I add a third, and I calculate the potential energy between it and this one, and potential energy between it and this one. So I'm going to calculate the potential energy between each possible pair of charges. And then the potential energy of the system is the sum of all of those potential energies. So, a three-charge system, as I indicate here, Q1, Q2, Q3, then the potential energy is going to have the potential energy between this pair, potential energy between this pair, potential energy between this pair. You add up the potential energies for each one of those pairs, and that gives you the total potential energy. And of course, at that point, it's very clear it has to belong to the system, not to any one of them. This is a problem for doing a calculation, but I need to get to electric potential. We talked, go ahead, Erica.
Okay, so you said the potential energy is on the system and not on the ball. But then like you could say on the hand because we had someone dropping the ball, how would that work out? I don't know. You can't see it.
I didn't understand the question, Cynthia.
So you know how you were talking about like the potential energy that was on the system and not on the ball?
Mm-hmm.
And then like you said, so like the ball would be the one dropping, like not the ball, the hand would be dropping the ball. So like how would that be like with this potential energy?
Well, I would, for the consideration of the ball Earth system, I'm part of the Earth.
Okay.
And so I'm just part of the everything that the ball is interacting with that I call the Earth. So it's accounted for as me being part of the Earth.
Thank you.
Yeah. Calculating the electric potential is simply taking the electric potential energy per unit charge. So hence my per unit charge in italics there. So that means the electric potential V is equal to the electric potential energy divided by charge. Using the point charge rule, so this is only for point charge in red, K, Q1, Q2 over R, all divided by Q2. So that's the electric potential from a point charge. So this is for a point charge only. So we can calculate that electric potential. What's the symbol for the electric potential? V. What's the unit? Well, the unit is pretty simple. Potential energy over charge. So joules divided by charge, coulombs. So it's a joule per coulomb. And we give an abbreviation to that, equals a volt. Now life becomes interesting. The electric potential V has units of V. And now you can understand why people call the electric potential voltage. They say, what's the electric potential? You say, it's 5 volts difference. They say, so 5 volts. What's the voltage? It's 5 volts different. So that's why electric potential and voltage mean exactly the same thing. Voltage is just referring to the units. Just like when we measure current, we'll be coming up with measuring current. Current is also called the amperage because it's measured in units of amps. I surely hope the textbook doesn't try to make some distinction between current and amperage, but they did between electric potential and voltage for reasons I cannot argue because they're wrong and I'm right. Ask my wife. I always feel that way. So electric potential voltage is a measurement of the potential energy per charge. Keep in mind it's potential energy per charge. When we start learning about electric circuits, we'll be talking about the voltage, and sometimes we start thinking that's kinetic energy. No, it's not kinetic. It's potential energy per charge. So, already done all of those. Getting back to our clicker questions, maybe. Escape. Nope, that's not what I wanted to do. There, got back to the clicker questions. You can answer now. A point charge always naturally moves to a position of lower potential energy. That's what we had on the earlier slide. What does this tell us about the natural motion compared to electric potential? What's another name for electric potential? Okay, voltage. Okay. Oh, now she's going to have to log in. There we go. Okay. This is our last question. I'm going to have you turn to your neighbor and discuss it, and we'll answer in 1 minute. Okay, go ahead and answer second time because we are at the end of class time. James Brandon Gila. Just Brandon. Okay. After discussion, things truly went amok. Okay, we have that it goes to lower potential energy. So if we look at this equation here, potential energy is going down, right? And so if Q is positive, then voltage is going down. But if Q is negative, then voltage is going up. So the correct answer was positive moves to lower and negative moves to higher. So that one person, kudos.